So it's another topic, but still very combinatorial, with a little bit more of enumeration without bijections, so basically generating function equations and solving them. So alternative tableau, I will define soon enough. And the basic thing will be a recursive structure of this tableau, which is quite new. I mean, this tableau has been much studied by different means. Different bijections have been defined, but the first time that there's a very nice recursive structure that appears. So this enumerative applications, and then also bijections, because thanks to these recursive structures, we can do either enumerative applications or bijections, a bit like I did with the Motzkin, the well-labeled Motzkin path. So, short introduction, impressive slide. I'm sorry, it's a bit too imposing. So this is a statistical physics model called the asymmetric exclusion process, actually asymmetric simple exclusion process. So you have n sites. You can see 7 sites below. These sites can be either occupied, so the black ones, or empty. And you define a Markov chain, in fact, for probabilists. So where's the pointer? Okay. So a position, so each time unit, if you want, some things can happen. Either a particle goes to the left, so it has to be empty here to go to the left, or it goes to the right, or of course it has to be empty. There's almost one particle per site. Or it can enter, so this means that there will be a particle here and this will become occupied, okay, from the outside of the outside world. Or if it's occupied, it can go on the left, etc. So this defines a statistical physics model that appears in many, I'm not very familiar, but many different situations can be modeled by some particularizations of this model. And so as a Markov chain in probability, we know that, so Markov chain means the states are the possible configurations of occupied states and occupied sites and non-occupied sites. So this will be coded by 0, 1, 1, 0, 0, 1, 1. Okay, so there are 2 to the n states. And what I define with this jumps of particles defines, in fact, you have to be more precise than I was, but it defines a Markov chain. And it is known that for these Markov chains, there are stationary probabilities, so that in the long term, the probability to be in a certain site will be something that's well defined. Okay, so it turns out that these probabilities can be interpreted combinatorially in many cases. But how to find them? So what is the probability to be in a certain site tau? So as I said, tau is a list of zeros and ones. So the one answer is a very physical answer, if you want. This kind of ansatz is very known in the physics literature. So it says that if you can find 2 matrices D and E, so this would be infinite matrices, okay? And 2 vectors, so W would be a row vector, if you want, infinite, and V a column vector. So if you can find such matrices and vectors verifying that the product of these matrices, so DE equals QED plus D plus E, so that the row vector is sort of a left eigenvector for W, for alpha E minus gamma D, etc. And the same for V. If you have these relations, if you can find such matrices and vectors, then you can express this probability Pn of tau by these things. So this just means that you take D if the site is occupied, okay, because it means tau I equals 1, so that 1 minus tau I equals 0, yes, and you will take E if the site is not occupied. So it's just one product of D's and E's, okay. Take D if the site is occupied and E if the site is empty. So Pn of t is equal to this big matrix product of D and E. You take a row vector, a V vector, the vector V, so it gives you a real number, and you divide by Zn, which is just the sum over all of these stuff, just to normalize things, okay? Because these are probabilities and they must sum up to 1 in the end. So it turns out I will not be, this has a relation to alternative tableau. I will not be too specific, but it's really the origin of why they were created. I mean, one of the origins. So now we define alternative tableau. So you take a Ferrer's diagram, so it means a staircase shape, except that I allow empty columns and empty rows at the end, okay? So this is another way to see it, is to make a path with east and south, west and south steps, okay? And then fill like this and put some cells in, make a grid inside, okay? This is completely determined by a certain path like this. And I will label, in fact, rows and columns by 1, 2, 3, 4, 4, increasing along this path, okay? Here I took the integers from 1 to 13, but in general, I will have any possible sets of integers, okay? As with the well-labeled Motzkin path before, okay, I could label by something else than the first integers. So sometimes I will put, they correspond to rows and columns, and for better readability, sometimes I will put them on the other side. So this is exactly the same, except the 7 was put on the other side of the row, etc. But you have to imagine that this, I didn't put these things at random. They really depend only on the shape. Okay, the shape determines what numbers they are. Once you determine once you have the label set, the labels are really attached to rows and columns. So alternative tableau has certain feelings of these shapes. Alternative tableau, so you fill by left arrows, up arrows, or you can leave also empty. And the condition is simply that if you take any arrow and if you follow it in the column or the row, then there's nothing in this direction. Okay, you can see all arrows. If you follow their direction, there are no other arrows, left or up, in this direction. Is it clear for everyone? Yeah. So some terminology. We call a free row a row which has no left arrow. Okay. So for instance, here you take 4 has no left arrow in it. 11 and 13. These are the labels of the free rows. Because the other ones, means 10, 7, 6, and 3, have a left arrow in them. Okay? Free columns is exactly the same, except it's just the symmetric thing, the reflected notion. So the free columns will be the columns with no up arrow in them. So here it's 1, 2, 5, and 12. Okay? So free rows, free columns. And free cells. Free cells is a cell which is not filled, so it cannot contain any arrow. Plus, there are no arrows that point to this cell. Okay? So in this case, you see these ones are not free because this points. This one is free because there is no arrow here, there or here that points to it. So I will label it. I will say that 4, 12, the coordinates. Okay, the cell 4, 12 is a free cell. You have also 11, 12. Okay, 7, 8, and 4, 5. I think that's all. There are 4 free cells in this particular alternative tableau. Okay, so we have free rows, free cells, and free columns, and these are notions that are important in the, as we'll see, I will show in the connection with the ASEP, with the asymmetric extremes. So just A of n, the set of alternative tableau, Aij, those that have I free rows and j free columns. And I will put an asterisk if I don't care about the number of columns, so that I star of n are the tableau with I free rows and any number of free columns. Okay, and the same with A star j. This packed tableau is a tableau with the maximal number of arrows. So it's easy to check that if you have a tableau with positive Oh, sorry, I said the length. It's very important. The length, it's the number of rows plus the number of columns. So it's the number of labels that I use. Usually when you consider Ferrer's diagrams, you consider the number of cells, okay, which in the Young tableau literature. Here it's not this at all, okay. My length, my size here is the number of rows plus number of columns. This is really the good parameter. So tableau, Pax tableau is so of length n is a tableau with n-1 arrows, and it's easy to check that this is the maximal number of arrows that you can put in a tableau. There's no way to put n arrows in a tableau, and it's equivalently it's a member of either A01, so it has one free row and no free column here, or one free column and no free row. Maybe I should be more specific. Okay. Just because if you take number of free rows, number of free rows, I don't know, maybe I have another notation. So free rows of T plus free column of T. What do I want to say? Plus number of arrows equals the length, because each arrow corresponds bijectively to a non-free row or non-free column by definition of an arrow. Oh, okay, but of freeness, because if you have a free column, it means that you have no up arrow. So up arrows, in fact, correspond to non-free columns. So if you take the free columns plus the up arrows plus free rows plus the left arrows, it gives you number of columns plus number of rows. So it gives you exactly the total number. So that's why here, if you have n-1 arrows, the only possibility is that this sum is 1. Okay? n-1. So it means that you have either one free column and 0 free row, or one free row and 0 free column. Is this clear? Or just that a column is either contains a left arrow or is free. A row. Okay, rows are of two kinds. Either they contain a left arrow or they are free by definition.
You never have two left arrows in one
No,
row.
because of the condition that an arrow cannot point to any other arrow. If you follow an arrow, there can be nothing in its direction. So there is at most one left arrow in a row. Okay, so here is the connection. I will be quite fast with ASAP. So if you have a shape, you can also label it by E's and D's like this, putting E, D, E, E, E for columns and D for rows. And the thing is, if you have D, E, V, W that satisfy these relations that I give for the matrix ansatz, these commutation relations plus the boundary conditions, then you can express any word in E and D, okay? Well, it means just a sequence of D's and E's. In this, you can. So this means that if you have a word in D and E, D, D, E, whatever, you have the commutation relations, okay? So you can put all the E's to the left. The commutation relations is DE equals QED plus D plus E. So it's easy to see that if you have this, every time you see DE, you will write it as QED plus D plus E. If you do this every time you see D followed by E, you will manage to write any product as a sum of words of the form is at the beginning and is at the back. Just by pushing all the, thanks to this commutation relation, you can put all the is on the left and all the d's on the right. And if you do this, what this means that you will in fact have a sum over all tableaux. So the number of terms in your sum at the end will be the number of tableaux, and the numbers of E's correspond to free rows, D correspond to free columns, and Q, the factor Q's that appear every time you make these commutations, is exactly the number of free cells. I will not show it. I can show it at the end. It's very easy. I mean, this commutation relation really expresses what it means to be an alternative tableau. But I will not spend too much time on this. In particular, if gamma and d equals 0, so gamma and d, if you look at this, if gamma and d equals 0, here, you have that WE is equal to alpha inverse W. Okay? Just put this and put the alpha on the other side. Okay? And the same if, if delta equals 0, you have that dV equals beta inverse V. So if you use this here, so we know that the probability to be in state tau, if you have to multiply this word W by W on the left, by V on the right, and divide by something, okay? But with these particular relations, you can suppress all. If you have something like, we had WE equals, I forgot already, alpha inverse. No, it was alpha inverse W. What is it? It's not very important, but and maybe it's beta, but what? And you have also that dV equals beta inverse V. So if you take this word and you use these two relations by putting a W here, a V after, then you can make all the E's and can make all the E's and D's disappear, and some powers of alpha inverse and some powers of beta inverse appear. And these powers are exactly the number of F row. I mean, I don't explain it very well, but it's quite obvious here. If you use the relation WE equals alpha inverse V, that by multiplying this by E at the beginning, by W, sorry, at the beginning, and V here, you will obtain this sum. So what it means is that the probability in the particular case where gamma and delta are 0 can be expressed as a sum over alternative tableau. So it has some sort of combinatorial interpretation. So just to say last word on this, we can also express, for some other parameters, we can also express this as a sum over alternative tableau. But if you take the full model at the beginning, where I had 1, Q, and I alpha, beta, gamma, delta, then we don't know how to express combinatorially the probability. There exist solutions, meaning some people have found matrices. Some Japanese authors, 3 Japanese people, have found matrices that work very well, but we don't know how to interpret this solution in a combinatorial way. So this is what is related to Askey-Wilson polynomials. Their solution involves the Askey-Wilson polynomials, which are very famous, orthogonal polynomials. I'm going back to alternative tableau, and I will show the structure that I talked about. So first I will show some very elementary bijections. The first one is transposition. If you have an alternative tableau, you can just reflect it, exchanging rows and columns, and also in the process exchanging up and left arrows. And this is obviously well defined. Okay, just exchange these rows and columns. It's an involution. Okay, that's not a problem. And the free rows become free columns, and the free columns become free rows. So this is very elementary. Okay. A bit less elementary is this. So just look at the first line. The second one is exactly the same after transposition, like many things that will appear. If you do something for rows, you can do the same for columns. There is a bijection between, so these are the tableau with I plus 1 free rows and no free columns. No free columns, meaning in every column there is an up arrow. Okay? And the tableaus with 1 less free row and any number of free columns. And the bijection is very easy. So you take a tableau. So look, it has no free columns because you have an up arrow in every column. And then you cut the first row. It's easy to see that this first row has to be free. So you will lose a free row. So that's why you go from I plus 1 to I. And then what you obtain, it's a very easy verification, is a member of AI star of n. The other direction, you take a tableau like this, you just add a first row, and then you fill every free column, you put an up arrow so that it becomes not free. Okay, so if you take this, you look at the columns that would be free, this one, this one, this one, okay? And then you put an up arrow in the column 10, 3, and 2, which are the ones here. You just complete things so that nothing is free at the end. Okay. So this is very elementary, but it will be very useful. The second line is exactly the same, but transposing. Okay.
The empty column is considered as free.
By definition, I mean, there is no free, there is no up arrow in it. Okay. I mean, it's a particular case, but there is no arrow, there is no thing, so there is no up arrow. Okay. Question. So immediately you have some equalities between the different kinds of tableau, according if they have 3 columns, 3 rows. The first one, if you sum over all j here, this will give you a0 star of n, because a00 of n is empty, but this is a particular case. This will give you n. If you sum over all g, you will have any number of tableaux. So this says that a of n is equal to a0 star of n. Just elementary. This is after transposition, of course. 3 rows become 3 columns, etc. And then if you take j equals 0 here, you have a01 of n plus 1 equals a star 0 of n. And if you shift by 1, you have exactly this one. And then after transposition, this one. So maybe I should write this down because it's very elementary, but it gives some relations between different kinds of tableau according to there are 3 rows or 3 columns. A01. Because these are the elementary things, and now I give something less elementary, but that gives another relations between these different classes. So with the two, we have a complete recursive decomposition. This is the easy part, and next one is a bit trickier. So this is the big theorem. So you pick I and j 2 integers. Okay, that will be the number of 3 rows and columns. L, a certain label set. You can think of it as the integers from 1 to n. Okay, it's any set of integers. So there's a bisection between the tableau with I 3 rows, j 3 columns, which are labeled by L. Just means that, as I explained, you just take the integers in L and you put them along the boundary. And on the other side, you have sets, so a collection of I plus j tableaux that are packed. Packed are belongs either to this one or this one. Okay, so you have I plus j packed tableaux that are packed. I of them are in this set, the remaining of them are in this set, plus the labels of this packed tableau form a partition of the original label. So you will take the original label set and put it in different on the different tableau that you obtain. Okay, I will show an example immediately. Try to draw. The proof is really you take each of the I3 rows, and you manage to attach to it a packed tableau. Okay, and do the same for each 3 column here, and you will attach to it a packed tableau. So this will give you a. So how does it work? So for each 3 row, okay, I will define a packed tableau around here. It's quite easy. So 3 row means no left arrow in it. So the recipe is the following. You take this 3 row and you look, are there arrows in it? Okay. If there are no arrows, you will define the packed tableau as just this 3 row, in fact. So a very reduced tableau with just one empty row like this. Okay. But there's an arrow. Okay. So what you do is you remember the label of the column. Okay. So I will just here select rows and columns, and in the end I will take them and define the sub. So there's an arrow at the intersection with the column 9. So now you do the same with 9. I mean by transposition. You look in the column. Are there some arrows? So column 9, there are 2 other arrows corresponding to rows 6 and 7. And for each, recursively, okay, for each of the arrows that you find, you look behind it somehow, and you look, are there arrows? Okay, and you do this. Okay, there are a finite number of arrows, so this will stop. And you just remember all the columns and rows that you've been through. Okay, so here we went 4, 9, then we had 6 and 7, and finally with 6 there will be 8. So we selected somehow 4, 6, 7, 8, and 9. And now you take just the subtableau corresponding to this columns and rows. This will give you this one. It is clear for you just keep the cells that are at the intersections of one of these arrows of these rows and one of these columns. Okay. So here you keep an arrow if there's an arrow. You leave it empty if it's empty. Okay. I would probably do some other examples so it will be more clear. So corresponding to the free row 4, this packed tableau. It's packed, okay, so you can easily check that it gives you packed tableau. If you do the same for the other 3 rows, 11 has no arrow in it, so you just take 11 alone, okay. 13 also has no arrow in it, so you just take the corresponding row and that's all. Okay, maybe it's a bit complicated. So you do the same for the 3 columns, okay, it's the same thing but the other way if you want. 1 and 2 have no arrows, so you just select them. 5, there's an arrow in column 3, so you select it. And you see I keep the labels every time, okay, of course. And for 12, 12, 10, and that's all. You have this. So you have I-packed tableau here, which have 1 free row and no free columns, okay. And if you have J in general packed tableau, and the result is that you obtain all labels this way, okay. These are packed tableau, and this is a bijection. So I will show briefly. I will tell you how to come back. Coming back is actually easier. Coming back is just taking this and sort of merging them together so that the labels increase. So I defined it just for 2 tableaux, but it's associative and commutative. So if you can merge 2 tableaux together, then you can merge any number of tableaux, and it's the same process. So if you have 2 tableaux, T and T prime, such that their label sets are disjoint, okay, because we want to get from the 2 a tableau such that its label set is the union of these 2 labels. What you do is simply you look at you take all the labels and you put them. So it's not very obvious because of the convention to put them on the right, on the left. I mean the labels, but just take the labels and you label the shape so that if you label it increasingly, okay, that's the main thing. And if I corresponds to a row in one of the tableaux, it has to correspond to a row here. And if it corresponds to a column, it corresponds. So for instance, 1 will be like this down because 1 is a row here. Then 2 because it's a column here. And then 3 has to be a row because it's a row in this one, etc. Okay, you just take the information for these 2 to know if it's a row or not. And for the filling, you just take all the arrows in this one, all the arrows, you report them here, and that's all, okay? All the arrows here correspond exactly to one of the 2 arrows belonging to either one of the 2 tableaux. So this is just merging. You just use the labels to find the shape, and then you report the arrows that you have. And if you do this, you can do this for more than 2 tableaux, and you have the other, the inverse bijection that I had. So this main bijection, there's another way to define it, because I split this big tableau in a lot of tableaux, but you can split it in 2 tableaux. If you merge all the tableaux that have just 1 free row, okay, the packed tableau in A10, you can merge them together, and these ones you can also merge them together. So by the property of mergings, you will have something that has no free columns in here, and then you will have something that has no free rows. So this is it. So it's just a corollary of the first bijection. In fact, there's another bijection between the same set of tableaux, and now the pairs of tableaux, one of them has no free column and the other one has no free rows, and I corresponds to the I here, such that the two sets form a partition of the original set L. Okay, it's just instead of splitting everyone, you keep together the tableau. You merge together the tableau in A10 and the tableau is in A01. So this gives this in the previous case, just merging the two parts. Okay, I will hurry a bit. A first application of this. So this was the complete recursive decomposition, okay? Because now we managed to split a tableau in A of n in tableaux that belong either to A0 star of n or A10 of n. And then we can use these relations to find again tableau in A of n, so in A of n. So this will give in the end, as we will see, a complete decomposition. So we can give generating function equations, etc. Call a tableau symmetric if it is fixed through transposition. So this is a symmetric tableau. It's clear for everyone what symmetric is. Just if you transpose, it's the same. So it has an axis of symmetry, the main diagonal. Okay. It's easy to see that by the corollary, if you try to split it in two tableaux, you know, there's one that corresponds to the free rows and the other one to the free columns. These two tableaux will be transposed of each other because of the symmetry of the original one. So you can just keep one of them, and then, so this will give you the term A star 0 of n. And then to choose the label set, once again, it's easy to check that the labeled set has to be such that exactly one between I and 2n plus 1 minus I can belong to the set. Well, I will not go into detail. Just if you notice this, if there are n labels, there are two choices for every labels, 2 to the n. So this corresponds to the 2 to the n here. Well, it's a bit sketchy, but it's very easy to prove from the corollary before. So now some generating function equations. So I define these three generating functions corresponding to tableau with no free rows, and to packed tableau. Okay, you have the same function for A10 of n, of course, because of the transposition. Okay. So the different decompositions and bijections that I show will translate immediately in equations on these generating functions. So you have to be familiar, of course, a bit with generating functions first. So, for instance, B is the generating functions of these ones, okay, of the A0 star. A is the generating function of this one. So this relation translates at the generating function level into this, this differential equation. It's just writing stuff, okay. And the same, the relation between A01 n plus 2 equals A of n. If you write what it means on the generating functions, it means that the second derivative of C is equal to A. Okay. On the other hand, the corollary to the main theorem says that if you take a tableau, you can split it somehow into two tableaux. One is in A0 star of n, and the other one is in A star 0 of n. Of course, by transposition, the two are this generating function. So by the standard calculus on generating functions, you obtain that A of z is equal to B of z squared. And if you take the main theorem saying that you transform a tableau into a set, so set becomes exponential at the generating function level, of either tableau that are in A01 or tableau in A10, which have the same generating function, so that's why you have twice the same term, you obtain this equation. Okay, now if you take this and this, it will give you a differential equation, B prime equal B squared, and here you will have C, the second derivative of C is equal to exponential of 2C. If you ask, the first one is very easy, the second one you can also solve by hand or ask any software, mathematical software, it works very fine. So in the end, it gives you something that is very well known. Okay, that was also one of the motivations for studying this tableau. That the number of tableaux A of n is equal to n plus 1 factorial. So just can give you, if you take b prime equals b squared. So, and actually b0 must be 1, something. B0 is the number tableau. Yeah. So the solution of this must be, right, of this, something, teach calculus. I think this is the solution of this differential equation. So if you expand this, the coefficient of x to the n, so we should put some z, of z to the n of over n factorial, the coefficient will be n factorial. Okay. So if you, because this is, b is shifted, b is this, and it's shifted correspond with respect to a will be n plus 1 factorial. Okay. So you can also find the same way that c of z is equal to minus log of 1 minus. You can check that this is the solution to the other differential equations. Okay. Write them because I think I will need them later. Some other things you can do is take into account, so some refined enumeration, the number of free rows and of free columns. Okay, you want to count, you define polynomial a(n) of x and y, where x and y mark the number of free rows and the number of free columns. Then you have this very nice expression, which you can check that if you put x equals 1 and y equals 1, you obtain n plus 1 factorial, so it makes sense already. So the proof is actually very easy. It's the same idea. So if you take the, so here I showed that a is equal to exponential of c plus c, the two corresponding to tableaus in a10, a01. But we showed that they correspond exactly the first to the number of free, I mean the number of this tableau here correspond to the number of free rows in the original tableau, and the other ones to the number of free columns. So you can mark it. So again, it's very standard in generating functions. You can mark them with x and y, and it gives you the good generating function. So you obtain exponential x, a10, exponential y. But as I showed here, this is c of z. Okay, so this is minus log of 1 minus z. So if you do the calculation, this will give you exponential of minus x plus y log of 1 minus z. If you put all of this together, you can expand. It gives you power series, and you can expand, and you really obtain this easily. It's really, you can do even more complicated. So add also the number of rows. So not only the number of free rows, but the total number of rows, and you obtain a much more complicated expression like this. But the idea is really exactly the same. You have some differential equations that you solve, and then you use the main theorems. And Maple, yeah. Actually, I knew the solution because of the relation with permutations. So you notice that a of n is equal to the number of permutations on n plus 1 elements. So there are some bijections where this is known at the level of permutations. All these parameters have meaning in permutation as some statistics on permutations. So this, at least for y equals 1, was already known. Okay. Another, so very quick theorem to show that the power of this method, because this is a theorem, okay, the number of alternative tableaux of length n, where you put a weight 2, in fact, on all arrows, okay? So you can have blue arrows, let's say, and red arrows. Whether they are, we don't care if they are left or up arrows, okay? Each of them can be colored in two, with 2 different colors, okay? And so Cortell and Williams gave a quite long proof of this, but with the structure theorem, we can be very fast. So if we write a tilde, the generating function of this colored tableau, and the same we will write c tilde for the packed tableau with these colors. So, as I said, arrows correspond to non-free rows, so and to non-free rows or columns. So this is the same as the alternative tableau, so that all non-free rows and non-free columns can be colored, okay? Because non-free rows and columns are the same as arrows. So this is an additive parameter, so you can really write, as in the non-colored case, you can write the same equations, okay? But now set tilde is quite easy. So set tilde is the generating functions for packed tableau, where the arrows can be colored by 2 colors. But packed tableau, by definition, there's only one row or column that is not free. All the other ones are free. Okay, so if you have a given normal tableau, to color it, there are 2 to the n-1 ways to color it, because there are n-1 arrows in it. So if you look on it gives you exactly this. So C of 2x is the generating function of in fact 2n a01 n, but if you divide by 2, you will have 2 to the n-1 a01 of n, which is exactly the number that's obvious. So this is, because of the expression for z, this is minus log of 1 minus 2x over 2, and then you plug it here, and you obtain 1 over 1 minus 2x, and this is exactly the generating function of these numbers. Okay, so immediately you don't really have to think, you obtain all these kind of theorems here. So now we'll be quicker on the bijective part. So I want to find a bijection with permutations, and as in my previous talk, there are trees as intermediate objects, because trees really encode immediately the recursive structure that I gave. So what are these trees here? They are labeled trees, but this time labels are also permitted on the internal nodes. All the nodes can be labeled, such that, so they are rooted trees also. Each white vertex is minimal. Minimal, I mean that it is smaller than all its descendants. Okay, it has a smaller label than all its descendants, meaning the children and children of its children, etc. Okay, so it's not really alternative tree. I mean, it's not a local condition. It's really all the children, all its subtree. So each white vertex is minimal. Its sons or its children are black and have decreasing labels from left to right. So it is a plane tree. So it's drawn in the plane. And you have dual conditions if you want for black vertices. They are maximal, they have white children, and their label are this time increasing from left to right. Forest is just a collection of trees where you dispatch the labels the way you want. So I will be fast here. This is an example, okay? So now the roots are up, because last time the roots were down. These trees are oriented this way now. The children are below their father. So you see black and white vertices alternate in each branch, okay? And if you have a black vertex, then its child has to be smaller and all its children have to be smaller also. So this, here you see that 4 is smaller than all the elements here, 9 is bigger than all its elements, etc. So this is a plane forest. And there is a bijection between alternative tableau of size n and plane alternative forests with n vertices. So I will, it's actually very easy. The decomposition that I gave, the structure theorem, really gives you each time the children, etc., recursively. So each of these trees in the forest correspond to the packed tableau that you obtain in the main that you get in the main theorem. And then if you do this procedure of cutting rows and columns, you will obtain, it's like cutting at the root and you will obtain subtrees, etc. It's really immediate. There's nothing to check, really. This forest can be also drawn in a quite nice way. Okay. So you draw them, but this time you first write all the labels, 0, 1, you write them on a horizontal line, like I did for matchings before, okay? You just write increasing labels. And what I call alternative arc diagram, so alternative means this first condition, so we'll have some labels like this, 0, 1, 2, 3. Alternative means that at each, so arcs are just, what I call arc as just normal arcs between two different points, okay? Alternative means that at each label, all the arcs have to go into one direction. There will never be a configuration like this. You cannot have a vertex where there's an arc going to the right and an arc going to the left. So it's alternating, if you prefer. So as a graph, it will be a tree. So this would qualify, for instance. Okay. This verifies the first two conditions, because if you consider it as a graph, it's a tree. And this condition means that if you take any arc except this one, so this one will always be present. But if you take outside this one, if you take any arc, then it will be on top on one side, and it cannot be on top. So on top means locally that this one is going here, this one is going further, this one is going even further. On top means the one that's going the furthest. Okay. So the condition means that on one side it has to be topmost, and on the other side it cannot be topmost. So I drew this with so there's an easy bijection with plane alternative forest. It's just another drawing of the forest and just rephrasing the conditions. Okay. So this is a complicated example. So I oriented, so the arrows I added are from the topmost side of the arcs to the non-topmost sides, that you can see more easily. Okay. So because by the third condition, there's exactly one. Where's the? Okay. For instance, it's this arc is topmost here. Okay, and it's not topmost there, so I oriented it in this way. Okay, from the topmost side to the nose. Okay. So why is it nice? Because you can see something that I didn't talk about, the free cells. Okay, I did everything with free rows and columns, but here you can see free cells, and they correspond to outcrossing arcs. So, okay, don't read the definition, but outcrossing means that two arcs that are crossing plus the arrows go this way, go to the outside. Okay, so you have a crossing of arcs, but a particular crossing so that the arrows go from this to the outside and from this to the outside. Okay, like something that's not good. This one here, okay, with this arc and there, it's not a good crossing, like because the arrows, this arrow doesn't go the right direction. Okay, and it's a fact that outcrossings correspond exactly to free cells. If you compose all the bisection, they correspond to free cells. And tableau. So I'll go tableau with no free cells are counted by Qatar numbers, which is a famous, one of the first results of alternative tableau. But meaning no free cells by the different bijections means no outcrossing, okay, by this proposition. In fact, no outcrossing implies no crossing at all. So there can be no crossings in this diagram. So you would have something like this, okay. And what you obtain are some trees that are that have been known for quite some time. Are called non-crossing alternating trees, which are just trees, and alternating is this condition. And they are very easily put in bijection with binary trees. I'll give it because I'll also use it tomorrow, actually. So just if you have something like this, you have automatically this arch. So if you delete it, you replace by a vertex in here. Okay. Then you have on one side you have another arc like this, which is topmost, and you replace it by simply a vertex. And here you have this one. You delete. You have this, and this one on this side that you delete. So this is very sketchy, but you understand that it's really another very close to binary trees, which are counted by Qatar numbers. Okay, I will not think I will stop here because I already. It's really easy if you have a plane alternative tree. It's very easy to do some sort of traversal of the. Just reading the labels in a certain way will give you a bijection with permutations, and this bijection is already known. Actually, it was already done twice in the literature, but this shows that in fact this was the same bijection that's been defined, and it's also equivalent to this one. Okay, and I think that's it. I will stop here. Thanks for your attention.
Any questions or comments?